Hello, and welcome to the notes on data representation. What a way to start the year. Who's pumped? Come on, let's do this. All right. So, first things first, layers of a computing system. So, this is kind of how we're going to progress through the course. Computers are like onions or ogres or parfaits. They have layers. And you can't really talk about all the layers at once. There's too much going on. It's overwhelming. So what we're going to do is we're going to focus at one layer at a time. And we're going to start at the most basic layer, which is the information layer. We're going to learn how that layer works. And then when we move up to the hardware layer, we're going to take the information layer for granted. And we're just going to say like, okay, we know that it's all working. We're not going to worry about the details because now we're focused on the hardware level. And then the same thing with programming, same thing with operating system, application, communication. We're going to go through the layers, but once we've gone through a layer, from that point forward, we're just going to sort of assume that it works so that we can focus on the problems and the intricacies and the unique parts of the individual layer that we're on. All right, so information layer. This is really what we're talking about here is the data being stored using binary digits, which we're going to be talking a whole lot about in a little bit. Binary meaning 2, and those 2 digits are always going to be 0 and 1 for our purpose. All right, so looking at how information is actually stored on a computer, what that looks like, and some of the different tools and things that are used to handle that. All right, so once we get that done, we're going to move up to the hardware layer. All right, so that'll be the next thing that we look at. And the hardware layer involves things like logic gates. So we're going to look at how to design different logic circuits. So circuits, control flow of electricity. So how things actually kind of move around and how things actually happen, like what allows the computer to do what it actually does. We'll also take a look at things involving the CPU. We'll take a look at things involving memory, but generally the hardware that kind of makes the program run. All right, so programming. This is a programming course. We're going to be doing this actually. The programming is going to be kind of interwoven throughout the whole piece. Some of the programming we'll be doing in Python. The majority of the programming we'll be doing in Python. But we'll also look at things like assembly. We might have a chance to look at Scheme and a couple other languages that are out there. But programming is basically the instructions used to process and manage data. Okay. Then up above that, we've got the operating system. All right, so the operating system sort of manages all of the resources of the computer. It kind of controls what programs get to use the CPU at a given time, and it kind of juggles those back and forth. But it manages the resources of the computer, and that might be memory, that might be CPU, things like that. Manages the resources of the computer and helps us interact with the machine. All right, it would be a lot harder to do everything you do on a computer if it didn't have some sort of operating system. All right. Application layer. All right, so this is when you're writing programs that actually do things and solve problems. So the application layer are the programs that help us solve real world problems. All right. And problems, I don't mean like problems like, oh, there's a problem, we've got to fix it, but like, Photoshop is at the application layer. It allows us the ability to manipulate photos and do all sorts of different, animation type stuff. That's at the application layer. It's not like a problem, but it enables us to interact and kind of complete tasks in the real world. And then last but not least is the communication layer, which is when we start sharing info between different computers. So all of those initial layers are all happening within a single computer. And then eventually we get to the communication layer where you start communicating between different computers and sharing information across different computers. All right. So first things first, let's talk about kind of this information layer. And we're going to talk about the idea of analog versus digital information. All right. So analog data, continuous and infinite, digital data, discrete and finite. So let's kind of talk about what that really means there. So analog data is usually what we see in the natural world. So in this beautiful black and white photocopy, you can see the variations of color in that rainbow there. All right. The colors sort of blend into each other, and there's almost an infinite number of colors as you move across the different wavelengths. So infinite number of colors, smooth transitions. All right. Versus over here, this is kind of like a color swatch. All right. We have a finite number of colors, and each is discrete. So we're going to talk a little bit more about how colors are represented in computers in a little bit. But sneak preview, it's based on the amount of red, green, and blue light that's being made up of each color. And those red, green, and blue lights can take values from 0 to 255, which means there are 256 possibilities. So if you've only got those three levers, red, green, and blue, and each of them can only go from 0 to 255, there are a limited number of unique combinations you can create. All right. Now, that number is rather large. It's 16,777,216 different colors. So there are a lot, but it's finite. And you don't have that same restriction when you're talking about the natural world and wavelengths of light. So same kind of idea here, with like a clock. This jumps between values, and this continuously moves across values. Right? And you may have like seen this sort of thing in like a math class or a science class when you're kind of differentiating between like things that can be measured versus things that you're counting. Right? And that's kind of like one of the major differences. Like, are you measuring it or are you counting it? All right. So the digital data is what we use in the computer world. The analog data is what primarily exists in the natural world. Now, the goal when we're using computers is to represent enough of the infinite world, right? Because it's infinite, we can't represent all of it. On a computer to satisfy our needs. Okay, it would help if I actually slid that up so that you can see what I wrote. But represent enough of the infinite world on a computer to satisfy our needs. So what exactly does satisfy our needs mean? Well, that depends. And that's where there's actually like interesting intersections between like computer science and biology or computer science and physics. For example, like audio files that you listen to on the computer are sampling from a sound wave, right? So periodically they take measurements of the sound wave to see what the amplitude of the wave is, and then they broadcast that out. The more samples you take, the closer it is to a honest representation of the wave. So when we do these computer files, it's based on like what the human ear is actually capable of detecting. There's no point in sampling at a rate greater than that because your ear is not going to be able to tell the difference. At least the human ear is not going to be able to tell the difference. Same thing with like video. All right. Video is really just distinct, discrete images placed one after another in an order that makes sense. Most video is at like 30 frames per second. So that's 30 individual pictures kind of lined up one after another per second. We don't need to go higher than that because that's going to look like smooth, crisp motion to the human eye. So there's all of these sort of interesting, studies of like, all right, so what do we have to do to represent this analog data in a digital format? And we kind of use the limitations of the human faculties, sight, hearing, and so forth, to kind of decide what those need to be. If you want to be really like dorky, you could actually say that when you listen to music on a computer, you are listening to 0% of the music. All right, so first of all, it's not a very good joke, but why 0% of the music? Because you're sampling from an infinite wave. So even if you take 1,000,000 samples, 1,000,000 over infinity is 0 if you've done anything with like, limits or math like that. So technically, because you're only taking a portion of an infinite wave, you're really not taking anything of it. So when you listen to music digitally, you're listening to 0% of the music, even though it doesn't sound like 0% of the music. Mathematically, technically, it's 0% of the music. All right. So with that in place, let's talk about this idea now of binary data. All right. So we've got to store things in discrete states on a computer. How do we start storing things on the computer? All right. We do that through binary data. All data in a computer is stored using transistors, which are like switches. All right. And this is where you're going to want to watch that video that is linked in the assignment. So there's a link to a video, and that will talk about switches. But primarily, transistors have only two states. They're either on, emitting a high voltage, or off, emitting no voltage. Okay. So what we've got going on here is here the switch, is on, here the switch is off. And what basically happens is there's sort of this range of voltages so that it doesn't have to be as exact. And as long as you're in this range, this might be the high range for voltage. And over here, this might be the low range. All right. And that way, as long as the voltage that's going through the switch is in this range, it's considered off. If the voltage going through the switch or the transistor, not switch, transistor. If the voltage going through the transistor is in this range, it's going to be turned on. If the voltage being applied to the transistor is in this range, it's going to be turned off. So one of the questions is like, all right, I can apply any amount of voltage. Why am I limiting myself to just on or off? Why not like measure the voltage, and then I could better approximate, the analog world. So if you ask yourself the question, why only two states? All right, so give it some thought for a second. All right, have you given it some thought? All right, good. So the main reason is, one, it's cheaper to make switches that only have on and off, and probably more important, and more reliable. All right. To create computers that only have to distinguish between two states, on and off. All right, so it's going to allow us to make things cheaper. It's going to allow us to make things more reliable. It's going to allow us to make things quicker. All important properties when you're talking about a computer. All right, so all the data in the computer is stored using these transistors. So how exactly does that actually work? So a transistor is a switch. It can be on or off. How does that then translate to actual data that we're storing? All right, so we can use these switches to encode information. So we're encoding information with ones and zeros. We have a bit, which is the smallest storage unit on a computer, and it stores either a 0 or a 1. A 1 represents the transistor being off. The 1 represents it being on. So we're only storing a 0 or 1, but we can use that 0 and 1 to represent different things. All right, so let's say I wanted to represent whether you passed or failed a course. All right, well, a 1, when the switch is on, could represent that you passed. And a 0, which is when the switch is off, could represent that you failed. So the switch is only on or off, but how we interpret that switch being on or off can be, oh, you passed or you failed. Now, let's say we wanted to do something a little more complicated. Like we didn't want to just know whether you passed or failed. We wanted to know, did you have an A, B, C, D, or F? If we had 5 separate switches, we could think of each of those switches as representing a letter. So let's say the first switch is the A switch. When this one is on and the rest of them are off, that would represent the letter A. And then we could keep going down. We could do the same thing for B, C, D, and F. With B, only the second switch is on. With C, only the third switch is on. With D, only the fourth switch is on. With F, only the fifth switch is on. And again, all we're dealing with is switches that are either on or off. We're considering on to be a 1. We're considering off to be a 0. And then we're assigning meaning to that sequence of zeros and ones. So if I see this sequence of zeros and ones, I know it's an A. If I see this sequence of zeros and ones, it's a B, and so on and so forth. All right, so this is how we can start to encode information into a computer using very simple on-off switches. Because at the end of the day, everything that a computer does is basically these on-off switches. So the kind of thought question here is, can you come up with a different encoding, a different pattern of ones and zeros to represent A, B, C, and D, and F that uses fewer bits? So we just did an example that used 5 bits. Can you come up with a way of encoding those letters that uses fewer bits. So instead of using 5, can you do it using 3? Can you use it doing 2? Can you use it doing 4? Like, how low can you go? So what I would do if I were you right now is I'd pause the video and I'd give it a shot, because I'm about to show you an example, but it's useful for you to actually think this out and try it. All right. So I'm assuming you've paused the video. I'm assuming you gave it a shot. Let's see if you came up with the same thing that I came up with. So fewest bits I was able to use was 3. And this is how I did it. All right. You might have done it in a different order, but if you came up with 3, I'm guessing you came up with something pretty similar. So this could represent an A. I could have this represent a B. I could have this represent a C. I could have this represent a D. I could have this represent an F. Now, your ones and zeros might look different than mine. That's fine. But the idea here is that each letter has a unique sequence. All right? So we can tell the difference between all of these because none of them repeat. All right. So this sequence is different than this sequence, which is different than this sequence, which is different than this one, which is different than this one. So we've still represented all 5 letters, but now we've done it with only 3 bits. We went from 5 bits to 3 bits, which is good because it saves time and money. We need less bits and we need less switches that we need to flip on and off because we're representing it with 3 instead of 5. Both good things. All right. So where are we going with all of this? All right. We're now seeing that we can represent things with these sequences of ones and zeros. All right. That brings us to representing numbers in computers. All right. And we represent numbers in computers using something called base 2, right? Which is an alternative way of representing numbers that only involves ones and zeros. So you should be familiar with base 10 because it's the number system you've used your entire life. So let's pretend that you have the number 2,193. All right. If we go back to elementary school, you probably learned that when you have bigger numbers, each number has its own place. So this right here is the ones place. This is the tens place. This is the hundreds place. And this is the thousands place. Okay. What you probably didn't learn in elementary school is that the ones place can really be thought of as 10 to the 0. All right? Anything to the 0 power is 1. The tens place can really be thought as 10 to the 1st. The hundredths place can be thought of as 10 squared, and the thousands place can be thought of as 10 to the 3rd power. Notice the base stays the same, and the base is 10 because it's the base 10 number system. But as you move places, the exponent changes. We go from 0 to 1 to 2 to 3, which means that this number 2,193 could be written as 2 times 1,000, because it's in the thousandths place, or 2 times 10 to the 3rd, plus 1 times 100, or 1 times 10 squared, plus 9 times 10, which again is 10 to the 1st, plus 3 times 1, which again, 1 is 10 to the 0 power. All right, so these two are equivalent, and this is sort of the breakdown, and this is what it means to be base 10. Each digit is to a different power of 10. 10 to the 0, 10 to the 1st, 10 to the 2nd, 10 cubed. All right? We're going to take that same exact logic and apply it to this number down here. all right? Because this is not 10,111. It's binary 10111, right? Now, much like this had the ones place, tens place, hundreds place, thousands place, all right? When we're dealing with binaries numbers, we have the ones place. Now, we don't have the tens place because our base is different. We're no longer base 10, we're base 2. So this is actually going to be called the twos place. All right? And this isn't going to be the hundredths place. It's going to be the fours place. And this is going to be the eighths place. And so on and so forth. This is going to be the sixteens place. All right. Now, where are those numbers coming from? Well, the 1 is the same, all right? Because we just said that anything to the 0 power is 1. So 2 to the 0 power is 1. This is just 2 to the first power. This is 2 to the second power. This is 2 to the third power. This is 2 to the fourth power. All right. So same idea. It's just our base is different. Instead of our base being 10, our base is now 2. But each time we move and add a digit, we add 1 to our exponent. Now, if we want to know what is this number equivalent to in base 10 or in decimal, we can do the same sort of thing we did up here. All right, we can say, all right, 1, because that's the actual digits that's in the number, times 16, because that's the place that it's in, plus 0, which is just going to wipe it out, times 8, plus 1 times 4, plus 1 times 2, plus 1 times 1. So same exact idea, but now we're looking at it with the powers of 2 instead of the powers of 10. And when we do that, if we add this up, 16 plus 4 is 20, plus 22, not plus 22, plus 2 is 22, plus 1 is 23. So this is 23 base 10, or it's 23 in decimal. So 10111 is the same as 23 base 10, sort of in a decimal number system. All right, so let's practice doing some of these. All right, so what I'm going to do is I'm going to write a bunch of numbers in base 2. You're going to pause the video, convert them to base 10, then you're going to check to make sure that you got the right answer. Now, in theory, could you just watch the video and not do it? Yes. How do you think that's going to go when you have to do this on a test? So this is where being in a college class and showing some maturity is going to be helpful. So pause the video, take your time, try these out, and then check your answers to make sure that you're getting what you should. So hopefully you paused the video. And if you have, and now you're wondering, did I get these correct? All right. 101,001 in base 2 is the same as 9 in base 10. 01000 is the same as 8 in base 10. 11111 is the same as 31 in base 10. 101 in base 2 is the same as 5 in base 10. And 102 is the same as 2 in base 10. Now, if you didn't get those answers, just remember that if we kind of go through this, this is the ones place, this is the twos place, this is the fours place, this is the eighths place, this is the 16th place. So you can think of these as your switches, and if it's a 1, you're adding that value. If it's a 0, you're ignoring that value. So on this very first one, you had a 1 on the 8 and you had a 1 on the 1. So 8 plus 1 is 9. On this one, the only one you had on was the 8. On this one, it was on the 16, the 8, the 4, the 2, and the 1, which is why you got 31. On this one, it was only on the 4 and the 1. On this one, it was only on the 2. So that's where all of those answers came from. And now that you know this, you can appreciate this very classic computer science joke. There are 10 kinds of people in the world, those who understand binary and those who don't. Because it's not actually 10, it's a binary 1, 0, which is equivalent to the number 2. So good. So very good. All right. Next, you may remember this little magic trick that I performed early on. Binary numbers are the secret of how I did it. All right. So I basically just asked you, a little refresher, is the number in this column? 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 And then I was able to instantly tell you what the number was. That's because those columns were basically a binary equivalent. All right. So the trick to this whole little, pulling back the curtain on this trick was if the column contains the number, it's equivalent to a 1 in the binary representation. All right, so for example, if I was doing the number 23, all right, there is a 23 there. There's no 23 here. There's a 23 here. There's a 23 here. There's a 23 here. So that tells me that it's the binary number 0, 1, 1, 0, 1, 1, 1. And then once you've done enough with binary, you can very quickly in your head just be like, oh, 1, 0, 1, 1, 1, that's 23. So that was the number that must have showed up. So I was in fact not a psychic. I was just good with binary numbers. Sorry to disappoint you, but as with most magic tricks in life, they're not what they seem. All right. So we talked about converting from decimal. Nope. We talked about converting from binary to decimal. How do we convert from decimal to binary? I'm giving you a decimal number. I want to know the binary representation. All right. So let's see how we could convert the number 47 and figure out what is the equivalent number in binary. All right. So the first approach we're going to take is something called the greedy algorithm. All right. All right. And the greedy algorithm is basically where we try to take out the biggest number possible. So if we think about our powers of 2, 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, we know that those are 64, 32, 16, 8, 4, 2, and 1. The sooner you get comfortable with these numbers, the better, because they're going to show up again, again, and again, and again, and again, and again, and again, and again. All right. So when we're doing the greedy algorithm, we basically start with a number that's bigger than our desired number. So 64 is bigger than 47. All right. It's too big, which means we can't have a 1 in that spot because it represents too large of a number. Then we start working backwards and we say, all right, is 32 too big? No, 32 is smaller than 47, so that's fine. So we say to ourselves, all right, 47 minus 32 is 15. All right, and we put a 1 there because the 1 says basically we took away 32. We were greedy, we took away as much as we could. And then we go to the next one and we say, all right, 16. Is 16 too big? And we're no longer comparing to the 47, we're comparing to the 15. And we say, oh, sorry, 16 is too big. All right, it's larger than our 15, so we have to put a 0 there. And then we get to our next one, which is an 8. And we say, all right, is 15 bigger than 8? Clearly it's not. So we're going to use our 8, and we're going to put a 1 there. And then we're left with 7, because we did 15 minus 8, and we got 7. We say to ourselves, all right, what about 4? Can we take 4 away? And we can. So we put a 1 there. And then we do 7 minus 4, and we get a 3. And then we say, all right, can we take 2 away? We can. And we say to ourselves, all right, 3 minus 2 is 1. And then we say, all right, can we take 1 away? Yeah, I mean, that's all we've got left. So 1 minus 1 is 0. And then there's nothing left over, so we're done. So we now know that 0, 1, 0, 1, 1, 1, 1 in binary is the same as 47 in decimal. All right, so that's what's called the greedy algorithm. You basically go through your powers of 2, you find the biggest one that you can still pull out, you pull it out, and then you just go down the line and repeat that process over and over and over and over again until you reach a stopping point. All right. Questions? You can't ask questions. It's a video. Don't be silly. Let's talk about the other approach, the division algorithm. All right. It's going to reach the same result. It's just going to get us there a slightly different way. All right. So to prove that it's going to get us the same result, let's use the same exact number. So I'm going to start with 47. And you might be saying to yourself, you've got all that space up above, Mr. Vona. Why are you writing it down at the bottom? You're going to see. All right. So what we're going to do is we're going to take 47 and we're going to divide it by 2. We're doing like old school long division here. All right. So how many times does 2 go into 47? You've got to be good at dividing by 2 to do this method. But 2 goes into 47 23 times with a remainder of 1. I told you it was going to be old school division. All right, there's 1 left over because it's an odd number. If you divide an odd number by 2, there's going to be 1 left over. If you divide an even number by 2, there's going to be 0 left over. So your remainder is always going to be 0 or 1. Now, what we do is we start going up and we keep doing this over and over and over again. We say, all right, what's 23 divided by 2? Well, that's 11 with a remainder of 1. Okay, what's 11 divided by 2? Well, that is 5 with a remainder of 1. Okay, what's 5 divided by 2? Well, that's 2 with a remainder of 1. All right, well, what's 2 divided by 2? Well, that's 1 with a remainder of 0. All right, well, what's 1 divided by 2? Well, that's 0 with a remainder of 1. Because 2 goes into 1 0 times, but there's 1 left over. When you get to 0 up top here, not when you get a remainder of 0, but when you get to 0 with your division, when you get to 0, comma, stop. All right, that means you're done. All right, and your answer, you read top to bottom. So the remainders were 1, 0, 1, 1, 1, 1. That is your base 2 equivalent of the number 47, which is exactly what we got when we used the greedy algorithm. All right, so either way is perfectly acceptable. I'm never going to require you to use a division algorithm or a greedy algorithm. I just care that you can convert a base 10 number into a binary number because any number that a computer deals with is going to be represented in binary. It's going to be represented in zeros and ones because remember, these zeros and ones are just switches that are either on or off. So if a computer wants to represent the number 47, it's going to do it by turning this switch on, this switch off, and these 4 switches on. And that's going to represent the number 47. All right. It all goes back to these switches and ones and zeros, and that's how we represent everything on a computer. So let's just do one more of these just to make sure that we're good here with the division algorithm. So we'll do the number 18. We're going to divide it by 2. All right, so 2 goes into 18 9 times with a remainder of 0. 2 goes into 9 4 times with a remainder of 1. 2 goes into 4 2 times with a remainder of 0. 2 goes into 2 1 time with a remainder of 0. 2 goes into 1 0 times with a remainder of 1. Again, I got my 0, so I stop. And then my final answer is 1 0 0 1 0. 1 0 0 1 0, base 2. And if you wanted to check yourself, all right, you could say to yourself, all right, well, this is the ones place, this is the twos place, this is the fourths place, this is the eighths place, this is the 16th place. These are the only two that have been flipped on. 16 plus 2 is 18, which is exactly what I was hoping for. So that tells me that I did it correctly. All right, so this is where we're going to stop the note video. And this is where you're going to get a chance to practice some of these problems and try a few different things. And we'll see how that goes. All right, so I hope this was helpful. And I hope it goes without saying that if you have any questions or something doesn't make sense, you just need to reach out, send me an email, set up a Google Meet, whatever, and we'll figure it out. All right, thanks and have a great day.